Hi all, welcome to my channel. So today we will see on induction motors, the power flow in the induction motors and the torque equation. So in the last session we have discussed about the principles of working of a three-phase induction motor and the working of three-phase induction motor on no load and on load. So the objectives of this session are to understand about the power flow, that is the power stages in the induction motor, and to understand relation between the torque, power and slip, expressions of a rotor current and EMF under running conditions, and maximum torque equation. Okay, fine. The first topic is that power stages in an induction motor. There is a stator and rotor, we know is that. Okay. Here the stator iron losses which consisting of eddy current and hysteresis losses depending upon the supply frequency and the flux density in the iron core. It is practically constant. So in the stator iron losses, they have two losses, that is eddy current and hysteresis losses. These two losses will depending upon this frequency, and here the in the stator the supply frequency is always 50 hertz, so it is constant. Okay. So the iron losses in the rotor is however negligibly small because the frequency of the rotor currents under running condition, that is normal running condition, is always small. Okay. So that is here, uh, the in the running conditions, what will be the frequency of the rotor, that is f dash is equals to s into f, which will be small quantity. The frequency will be like 2 hertz or else 3 hertz. So the iron losses in the rotor at the running conditions are negligible. So here this is the total rotor losses, copper losses, which is equals to, as it is a three phase, it is 3 into I2 square R2. I2 here representing the rotor current. Okay, this is the rotor resistance. Okay, so what are the different stages of the power development in an induction motor? Okay, here in the motor, first one, the motor input in stator, that is P1, this is the input we are giving at stator, and stator copper and iron losses will be there. After removing the stator and copper losses from P1, that is the input, motor input, you are going to get the rotor input, sorry, here the stator input, you are going to get the rotor input. From the rotor input, the rotor copper losses will be minused, then you are going to get the power mechanical developed in rotor, that is gross power. Okay, which is equals to, after that you will get frictional and windage losses. So after minusing frictional and windage losses from this PM, then you will get the rotor output, that is power output, actual power output. Okay. So here P1 minus stator copper losses is equals to P2. P2 minus rotor copper losses is equals to PM. PM minus frictional losses is equals to P out. Okay, this is the power flow. So the power stages in a synchronous motor. Okay. So it will be like the power input to stator minus the stator copper losses and iron losses, which is equals to rotor input minus rotor copper losses is equals to mechanical power developed minus frictional windage losses, which is equals to power. It is same as that of a induction motor. So here, so it is written in as like a classification model. Okay, so power input, which is giving, okay fine, we can come from here. Okay. So output plus frictional losses is equals to power developed, and power developed plus rotor copper losses is equals to rotor input, and rotor input plus copper stator copper losses and iron losses is equals to power input. So power distribution diagram from the induction motor, for the induction motor. The same diagram, but here we have to follow some notations. Okay. So PCS, that is copper losses, PF or else PI is an iron losses. So rotor input, that is P2, which is an air gap. Then rotor copper losses is PER. Here these notations can be written as our wish, but when you are solving any problem, you should follow only one notation. So here mechanical power is in PM, and it is also called as gross power, which is PG, and the windage losses is equals to PW, and the power output is P output. So here if you see in pictorial wise, okay. So here we are giving P input, that is a power input to the motor, and here you are getting a stator copper losses and iron losses in the stator here, and here you are going to get the rotor input to the rotor, and in this rotor copper losses, and here you are going to get a gross power and again windage losses, then the shaft power, which is actual output. So an induction motor develops gross torque TG due to the gross rotor output PM. Okay. Its value can be expressed either in terms of rotor input P2 or rotor gross output PM as shown in below. So we know that torque Tg is equals to P2 divided by omega s. So this one we have in a DC motors, when we have discussed, we have derived a torque equation, same thing like that. So here torque is equals to the power divided by omega s, okay, which is equals to P2 divided by 2 pi ns in terms of rotor input. So Pg is equals to Pm divided by omega, which is equals to Pm by 2 pi n in terms of rotor output. This is, and this is rotor input. The shaft torque TSH is due to the output power P output, which is less than PM because the rotor frictional and windage losses are there. Yes. So P output is always less than PM because PM will include the frictional and windage losses. So TSH is equals to P output divided by omega, which omega is nothing but 2 pi n. So the differences between TG and TSH equals the torque lost due to the friction and windage losses in the motor. So in the above expression, N and NS are in RPS. However, if they are in RPM, the expression of the motor becomes. So here Tg is equals to P2 divided by 2 pi N divided by 60. Okay. Which is equals to 60 by 2 pi into P2 by Ns, which is equals to 9.55 into P2 by Ns. Okay. Ns is nothing but synchronous speed. Okay. Not, I mean, that slip S. It is synchronous speed, which is in Newton meters. Okay. So Tg is equals to 9.55 into rotor input divided by synchronous speed, that is N into M. I mean, sorry, Newton meter. Okay. Which is equals to, it is in PM. Okay. So PM divided by N, which is equals to 9.55 into PM divided by N. Here this N is a speed of the rotor. This is a synchronous speed of the input. Okay, here this is an output, so this is a rotor speed. So 9.55 into power developed, mechanical power developed divided by the speed, Newton meters. So what is the torque at shaft? Torque at shaft is equals to the power output divided by 2 pi n by 60, which is equals to 9.55 into power output divided by n Newton meter. So the stator input is P1, which is equals to stator output plus stator losses, and the stator output is transferred entirely inductively to the rotor circuit. Obviously, rotor input P2 is equals to stator output. So rotor gross output PM is equals to rotor input P2 minus rotor copper losses. So this rotor output is converted into mechanical energy and gives rise to the gross torque Tg. Out of this gross torque developed, some is lost due to the windage and frictional losses in the rotor, and the rest appears as a useful shaft torque TSH. So these all the power flow we have seen in the flow diagram. Okay. Let n is an RPS be the actual speed of the rotor, and if Tg is in Newton meter, then Tg into 2 pi n is equals to rotor gross output in watts. Tg is equals to rotor gross output in watts, that is Pm divided by 2 pi n. If there were no copper loss in the rotor, then the rotor output will be equal to the rotor input and the rotor will run at a synchronous speed. But this won't happen. Okay. So Tg is equals to rotor input Pt divided by 2 pi ns. So from equation 1 and 2 we get rotor gross output Pm is equals to Tg into 2 pi n and rotor input P2 is equals to Tg into 2 pi ns. The differences of the rotor gross output and the rotor input equals to rotor copper loss. Yes. So rotor copper loss is equals to P2 minus Pm, which is equals to Tg into 2 pi into ns minus n, which is equals to slip speed. Okay. So rotor copper loss is divided by rotor input, which is equals to ns minus n divided by ns, which is equals to s. So we know this is a slip. Okay. So rotor copper losses divided by rotor input, that this is P2. Okay. PCU, P2CU, you can denote this. So this we know that is ns minus n according to the above below equation here, and the rotor input is P2. So if Tg this divided by this. Okay. So right, I will write there. Rotor copper losses by this equation. Okay. So Tg 2 pi and Tg 2 pi will get cancelled. Then you will be left over with ns minus n divided by ns. So ns minus n divided by ns is slip. We know that. Okay. So therefore, rotor copper losses is equals to S into rotor input. So we are indicating this with S into P2. Okay. Which is also called as power across the air gap. So this is denoting as fifth equation. Also, rotor input is equals to copper losses by S. So from this equation, we can say that P2 is equals to S into rotor copper loss. by S. Okay, rotor copper losses divided by S from this fifth equation. So rotor gross output PM is equals to input power P2 minus rotor copper losses, which is equals to input minus S into rotor copper losses in terms of rotor input. Rotor copper losses in terms of rotor input is this. Okay. So rotor gross power PM is equals to input P2, that is nothing but rotor input. Okay, rotor input P2 minus rotor copper losses. So here P2 minus S into P2 equation. Okay, what is this actually? This is a PM, rotor gross power or the mechanical power developed. Okay. So from this P2 we can take common and you will get 1 minus 2, 1 minus S. Okay, so here we observe PM is equals to 1 minus S into P2. Okay, so 1 minus S is nothing but which is also equal to N divided by NS. So here what's happening? Here PM divided by P2 is equals to 1 minus S, which is also equal to N by NS. So PM by hence rotor gross power divided by the rotor input is equals to rotor speed divided by synchronous speed, which is also equals to 1 minus S. So rotor efficiency, which is equals to N by Ns. Also rotor copper loss divided by rotor gross power. So here this I can write it as which is also equals to 1 minus S. Okay. So this I can put as equation 6. So we have already one of the equation, fifth equation, that is ECU, that is rotor copper losses divided by rotor input is equals to S. Okay. Now here PM divided by P2 is equals to 1 minus S. So rotor copper losses divided by PM. So now ECU divided by PM. How you will get that? Equation this divided by equation this. So you will get P2 by PM, I mean rotor copper losses divided by the rotor mechanical power, which is equals to S divided by 1 minus S. So the torque mechanical power and the rotor output. The important conclusion, that is, if some power P2 is delivered to the rotor, then a part of rotor input is lost in the rotor itself as a copper loss and appears as heat, and the remaining 1 minus SP2 appears as gross mechanical power, which including the windage and frictional losses. Okay, it is very much clear. So here PM is to P2 is to PM is to here, so it is a copper losses, I guess. Right, I think so. I will write it as gone, I guess. Okay, here this is a PCU. copper losses. Okay. So this you have to remember. See, for everyone who are studying about the induction motor, this relation should be always in your mind. Okay, that is P2 is to PM is to PCU is equals to 1 is to 1 minus S is to S. Okay, so this is an equation. So here the denotation is ER. So the rotor input power will always divided itself in this ratio. Hence it is advantageous to run the motor with as small a slip as possible. So till now we have gone through the power flow and the power equations, each and everything. So from this equation, we can find out, see, if we know slip, only slip is efficient, slip is enough. Okay, if you know slip and if you know P2, you can find out copper losses and you can find out PM with this equation. Okay, so from these two, if you get any two values, you can get another values also. So here now we will see that the rotor EMF and the reactance under the running condition. So let E2 be the standstill rotor induced EMF per phase. I2 is a rotor standstill current per phase. X2 is a standstill rotor reactance per phase. F2 is a rotor current frequency at standstill. But when rotor is stationary, that is S is equals to 1, the frequency of rotor EMF is the same as that of the rotor supply frequency. When S is equals to 1, you should remember, okay? The value of the EMF induced in the rotor at standstill is maximum. That is, E generated EMF in the rotor at standstill is maximum because the relative speed between the rotor and the rotating flux of the stator is maximum. In fact, the rotor is equivalent to the three-phase transformer with the short-circuited rotating secondary. So, this induction motor is resembles like a three-phase transformer where the secondary winding of a three-phase transformer is short-circuited. Here, what happening? We are in an induction motor. The rotor bars are short-circuited. So the winding of the rotor, we are short-circuiting it for self-starting. So in the same way, so when we take an induction motor, it resembles like a transformer. The transformer is looking like the induction motor is looking like that the primary is as such and the secondary winding is short circuited. So when so here rotating EMF and reactance under the running conditions. So we have discussed this here. And when rotor is stationary, that is S is equals to 1, the frequency of the rotor EMF is same as that of the supply frequency. Okay. So when the value of EMF induced in the rotor at standstill is maximum because of the relative speed between the rotor and revolving stator flux is maximum. In fact, okay, the rotor is equivalent to three-phase motor with a short-circuited rotor secondary. So we have discussed even this. So when rotor starts running, the relative speed between it and the rotating stator flux is decreased. Then the rotor induced EMF, which is directly proportional to the rotor speed, is also decreasing. Relative speed. So this rotor EMF is directly proportional to the relative speed. Where relative speed is decreasing, so the EMF induced in the rotor will also decreases. Okay, and may disappear although altogether if rotor speed were to equal to the speed of the stator flux. That is, if the rotor rotates at a synchronous speed, then the EMF induced in the rotor is equals to 0. Hence, for a slip, yes, the rotor induced EMF will be S times the induced EMF at standstill. Therefore, under running conditions, the rotor EMF is equals to S times the standstill rotor EMF. So, E2 is the rotor EMF at standstill and the ER is a rotor EMF at running condition. Okay. So, rotor EMF at running condition is equals to S times the rotor EMF induced at standstill. So, the frequency of an induced EMF will likewise become Fr is equals to S times the F2. So, this is a running condition. Rotor frequency at running condition is equals to S times the rotor frequency at standstill. So, due to decrease in frequency of the rotor EMF, the rotor reactance also decreases as XR is equals to S into X2, where ER and XR are rotor EMF and reactance under running conditions. Therefore, the torque is directly proportional to E2 I2 and cos pi 2. Okay. Here it is in running condition. So, it is ER IR cos pi R pi 2 or pi into IR cos, as ER is directly proportional to flux. So, where ER is equals to the rotor EMF divided, the rotor EMF per phase under running condition. So, IR is equals to the rotor current per phase under running condition. So, now ER is equals to S into E2 and IR is equals to as per V by I rule. Okay, so IR is equals to ER divided by ZR, which is equals to S into 2 S times the standstill EMF divided by Z is nothing but under root of R2 square plus SX2 whole square. So this is in a triangular way. Okay, this is SX2 and this is R2, this is Z. So ZR is equals to under root of R2 square plus SX2 square. Okay, this is a phasor diagram of impedance. So cos pi 2 is equals to R2 divided by Z. Okay, so R2 divided by Z is here under root of R2 square plus SX2 whole square. So you have to remember some formulas. Okay, so cos pi 2 always power factor of an induction motor is equals to R2 divided by Z. Okay, so therefore now T, that is torque, is directly proportional to S into E2, then R2 divided by R2 square plus SX2 whole square. One second. So from the equations only we will get it. Okay. So here, so we know that, okay, so torque is directly proportional to E R I R and E R I R and cos pi 2. So now we know E R, we know I R, and we know cos pi 2. So substitute all the values in this equation. So ER is equals to S into E2, IR is equals to ER divided by Z. Okay, here is equals to S into E2 under root of so and so. So substitute that value. Okay, and then cos pi 2 is R2 divided by this thing. So what happens when you substitute that? The denominator is both. Okay, fine. I will write directly so that you could able to understand better. Okay, so this is S into E2 into IR is S into E2 divided by Z2. So what happens? Under root of R2 square divided by Sx2 whole square into cos pi 2 is R2 divided by, again, under root of R2 square plus Sx2 whole square. So now here this root and this root will get cancelled because these both will become whole square if I only represent taking out of this. Okay. Now this square and this root will get cancelled. So we will remain with this part then, which is equals to, okay, previously I mentioned that here here the torque is directly proportional to E2, I2 and IR. So there is a E2, I2 and cos pi 2. So there is a difference between ER, IR, cos pi 2 and E2, I2, cos pi 2. Okay. So that is where we got, we will get the difference in the, when we are solving the equation. So this is E2, this is not IR. So this is E2. So E2 is directly proportional to pi. This is not ER. Okay, this is E2. which is directly proportional to pi is nothing but a theta flux here. This will be always constant, so this is also always be constant. Okay. So here what happens? So this is E2 and this is I2. So I2 is equals to S into E2. This will be only E2. Directly we can write it. Okay. So here this and this will get cancelled. Now the total equation you'll get S into E2 square into R2 divided by R square plus Sx whole square. So where K is a proportionality constant, so we have taken T is equals to K S into E2 square R2 divided by R2 square plus Sx2 whole square. Okay. So we know that E2 is directly proportional to pi. So where K1 is another constant, its value can be proved to be equal to 3 by 2 pi ns. Hence, in this case, expression for the torque becomes 3 2 pi ns into S into E2 square R2 divided by R2 square plus Sx2 whole square. Sx whole square. So here this is totally represented as Z impedance square. So at standstill, what happens? We know that S is equals to 1. So substituting here S is 1. So here K1 is equals to E2 square, E2 square R2 square plus X2 square because S is 1 here. So we know that the K1 is equals to 3 by 2 pi ns into E2 square R2 divided by R2 square plus X2 square. So under running condition, the torque of the rotor under running conditions is K into pi into S E2 square R2 divided by R2 square plus Sx2 whole square, where K into so and so, then the condition for maximum torque may be obtained by differentiating the both the expressions with respect to slip and putting it to equate to 0. Okay. So here, it is taken as y, that is R2 square plus Sx2 whole square divided by K pi S E2 and R2. So R2 by K pi S into E2 plus Sx2 whole square divided by K2 pi 2 E2 R2. So dy by ds is equals to minus R2 by K pi S square E2 plus X2 square divided by K pi E2 R square is equals to 0. Therefore, which we are equating it to 0. So this and is equal to this, or R2 square, because K pi and E will get cancelled. So R2 will become R2 square, which is equals to this S will go here. So S square X2. So R2 is equals to Sx2. So the condition is that when R2 reaches to slip times of Sx2, oh, I mean that the rotor reactance when it reaches to R2, then the torque is maximum. Okay, hence the torque under running condition is maximum at the value of the slip where S, which takes rotor reactance per phase equal to the rotor resistance per phase. So the slip is sometimes written as SB and the maximum torque as TB. Okay, so this is the slip which is responsible that taking the reactance to equal to the rotor resistance. At that slip we are getting the maximum torque. So slip corresponding to the maximum torque, S is equals to R2 by X2 according to the above equation. That is R2 is equals to Sx2. Okay. So in the running conditions, that putting R2 is equals to Sx2 in the above equation, here we are directly substituting the equation. So we will get, substituting the value of S is equals to, so we will get T max is equals to, that is maximum torque is equals to K1 into E2 square divided by 2x2. So K1 is nothing but 3 by 2 pi ns, whereas T maximum is equals to 3 by 2 pi ns into E2 square divided by 2x2. So from the above, it is found that the maximum torque is independent of the rotor resistance. So here the maximum torque is equals to E2 by 2x2. Here if we see, there is no R2 component in this final equation, in the maximum torque equation. So we can say that the maximum torque is independent of rotor input resistance. But yes, the slip which is corresponding to the maximum resistance is responsible for the uh, which is dependent upon the rotor input resistance. I mean stator resistance. Okay, rotor resistance. But this is a slip at maximum torque. Okay, so the slip we got at a maximum torque is this one. So here the slip is dependent upon R2, but whereas the torque is independent of R2. However, the slip or speed or the slip at which maximum torque occurs is determined by the resistance, rotor resistance. So as seen from the equation, the torque becomes maximum rotar when the rotor reactance is equal to its resistance. The torque becomes maximum when rotor reactance becomes equal to its resistance. Okay, and hence by varying rotor resistance possible only with slip ring induction motor, and the maximum torque can be made to occur at any desired slip. Okay, so this is only possible in the slip ring induction motor. See, by varying the rotor resistance we can get a maximum torque which is made to occur at any, I mean, a required desired slip. So we could able to get by varying the rotor resistance. Okay, which is possible only in slip ring induction motor. So the maximum torque varies inversely as a standstill reactance, hence it should be kept as small as possible. So we know that the torque is directly proportional to E2 and inversely proportional to reactance, that maximum torque. So here the maximum torque is inversely proportional to X2. So if this reactance is small, then the torque will be more. So the maximum torque varies directly as the square of the applied voltage. So from obtaining maximum torque at starting, so at starting, so starting we need to get maximum torque means that S is equals to 1. So where S is equals to 1, then X2 is equals to R2. The rotor resistance must be equal to rotor reactance. So rotor reactance must be equal to rotor resistance. Okay. And the rotor torque at any slip, yes, can be expressed in terms of maximum TB by this equation. So T is equals to TB by 2 divided by slip at maximum divided by normal slip plus slip at maximum divided by normal slip, where SP is a breakdown or breakout or maximum. So T divided by T maximum is equals to. So we know T normal torque and we know maximum torque. If these both equations we will divide, then we will get 2 into S into R2 into X2 divided by R2 square plus SX2 whole square. So by dividing numerator and denominator by X2, so we are going to get, so taking this as component A. Okay. So 2 into AS divided by A square plus S square. So this is a formula that you have to remember, that T divided by T maximum is equals to 2 into AS divided by A square plus S square. So Ts divided by T maximum is equals to 2R2x divided by R2 square plus XS2 whole square. Okay. So this is the target any slip and target maximum. So we are going to get here this is a, sorry, starting torque. Okay. So that is S is equals to 1. At here the slip will be is equals to 1. So here Ts by T maximum. Ts by T maximum is equals to Ta by 1 plus A square. So we know this equations already we have seen. So the summary is that we have seen that uh, TG and TSH, and we discussed about the rotor gross output PM and the rotor gross output PM rotor. Okay. And the torque maximum, torque at any slip, starting torque, everything. Okay. So the now quiz point we will see. So when applied, the rated voltage per phase is reduced to half. The starting torque of squirrel cage induction motor becomes dash of the starting torque with full voltage. Okay. So what is an answer? See, we know that torque is directly proportional to E square, E2 square. Okay. So what's happening here? This is 1 by 2 whole square. So what happens? It will become 1 by 4. So when the applied voltage is reduced by half, then the torque will reduced by 1/4, as the torque is dependent upon the square of the applied voltage. So Tg is equals to P2 by Ws. True? Yes. And the rotor gross output divided by the rotor input is equals to 1 by S, 1 minus S. Yes, true. So hope today's session have been understood to you. Today's is maximum the derivation part. So we have to remember the torque equation, torque maximum equation, and EMF equation. Uh, so these are very important to remember, so that you can easily solve the problems which are coming in the next session. Okay. So thank you so much.